Deforming solids. Different materials behave differently when subjected to a force. If we plot a graph of force against extension for a number of materials, we would find something like this for a spring. It obeys Hooke's law in that force is directly proportional to extension. This is as long as the spring is not loaded beyond its elastic limit. More about this later. A piece of polythene might have a line something like this. Initially it is quite hard to deform, it then stretches quite easily before again becoming harder to deform. An elastic band has a line like this. Initially it extends fairly easily, becomes slightly harder, and then eventually here becomes very difficult to deform. Let's look a little bit more closely at the elastic band. This is the line we get on loading the elastic band, and the graph is a force against a distance. So the area under the graph here represents the work done in stretching the elastic band. When we unload the elastic band, it would follow a slightly lower line, like this. We don't get quite the same contraction at the large force as we had to put in when extending the elastic band. The area under this line represents the work done by the elastic band as it contracts. So the difference between the two, this area here, represents energy stored within the elastic band, which is mainly as thermal energy. A piece of polythene which had been stretched would show hardly any contraction at all on release of the force, and would follow an unload line something like this. The area shown represents the work done in deforming the polythene, and also stored within the polythene, again mainly as thermal energy. The spring follows this line on loading, and returns along the same line on unloading. As long as it is within the elastic limit, the spring would return to its original length, and any energy loss within the spring is negligible. If a spring is loaded beyond its elastic limit, it would return on unloading along this line, and there is permanent deformation. So we can say that if a spring is loaded beyond its elastic limit, it is permanently deformed. This graph shows the behavior of a wire under stress. It is now a graph of stress against strain. Stress is simply the force per unit area applied to a material, where strain is the change in length over original length. These are covered in more detail on the video on Young's modulus. Up to point A, we have a straight line through the origin, showing that stress is directly proportional to strain. So, A represents the limit of proportionality. Point B here represents the elastic limit. Beyond point B there will be permanent deformation. The wire will now behave plastically and will be permanently stretched. Point C represents the yield point. The wire weakens at this point temporarily. At point D, the wire now starts to extend easily and displays plastic flow behavior. Point E is the ultimate tensile stress or breaking stress. At this point the wire will thin significantly, will weaken and finally break. This is the greatest stress that the wire is able to withstand. The stiffer the material, the steeper the line on the stress-strain graph. So if this line represents steel, we might get a line something like this for copper. Steel then is a stiffer material than copper. It needs a bigger stress to produce a certain strain. Copper is said to be more ductile than steel. It can be more easily drawn into a wire. A material which is brittle, such as glass, will break or fracture with little or no extension. So you see here we have a large stress building up with little or no strain, and then suddenly the glass just fractures or breaks. It is a brittle material.